Swayam Prabha. Digital India. Educated India.
So, hello everyone. Now, we will start a new topic in the blow room, which is characteristics of reserve box, and here we will try to derive the relationship of apparent density of the fiber assembly. So, fiber topped apparent density is extremely important, that we have discussed in earlier section in the opening and cleaning section. So, apparent density of fiber topped, how to calculate, here we will discuss. Okay. Now, if you see here, this is a photograph of reserve box here. In the reserve box, why reserve box is used? Because to get the continuous fiber supply for the next process, it is important to have the store in this reserve box here, but during the storage of the fiber, the upper layer actually apply load on the bottom layer, lower layer, and that it reduces the opening. So, apparent density it increases at lower section due to the load applied by the top layers. So, in the reserve box we must store the material, at the same time it affects the apparent density of fiber assemblies. So, that we will theoretically calculate the apparent density. So, we will start with the theory of compression proposed by Van Wyck, okay, for fiber assemblies. So, that will take that the equation. So, compressive pressure acting on the fiber assembly is derived, expressed by Van Wyck, was this is the P equal to C 1 E multiplied by m by rho square multiplied by 1 by T square, where P is the pressure on the fiber tuft, C 1 is a constant, E is the Young's modulus of fiber. So, fiber's Young's modulus is important because it helps, it is related with the bending force or bending rigidity. M is the weight of material, weight. Rho is the density of material, fiber density, like for cotton it will become 1.52 approximately, and T is the thickness of material stuffed. So, where that, as I have told, that the material, this is the material, how much thickness is there of the material which is being stuffed. So, that is the stuffed above the portion where we want to measure the pressure, compressive pressure, and this actually changes the apparent density here, apparent density it changes. So, apparent density will be higher at the lower portion than at the upper portion, considering their openness are same. Okay. So, for fiber assemblies in an infinite small is very small, okay, area if we take. So, infinitely small area where height is dH, okay, and weight is dm. If we take the small area with height dH, and if we take the mass here, it is a dm. Okay. P is the pressure from the top, upper pressure, and lower pressure will be P plus dP. This dP pressure comes from the mass of the fiber in that zone of height dH, infinitely small height dH. F is the frictional resistance between the fiber and the wall of the reserve box, because when we press the material against the wall, so the wall will actually insert some frictional resistance. So, that is F is the frictional resistance which acts as the against the load from the against the mass, against the load applied by the fiber mass. That means, it reduces the effective load, effective pressure on the fiber at the bottom. A is the cross sectional area of the reserve box. Now, if we try to equalize the force equilibrium equation becomes, if you see, A area is the area, P plus dP is the pressure at the bottom. This is the P plus dP, dP is the pressure exerted by the fiber mass of depth dH. So, A multiplied by P plus dP will be the force, upward force. Okay. Now, try to see the downward force. Downward force is the downward pressure is P, A multiplied by P is the downward pressure by the fiber above that mass, and dm is the mass of the fiber at that, or weight of the fiber, that load applied at the lower direction, bottom downward direction, minus F that I have already mentioned. It actually reduces the effective load downward. So, that is the balancing equation, and so if we simplify that, it will become A dP. So, AP gets cancelled. So, A dP equal to dm minus F, and now dm, how to calculate dm here? Dm is nothing but the weight of the material at height dH. So, here gamma is the apparent density of fiber at this zone, which is actually our target. We want to measure the apparent density at particular portion. So, dm equal to A multiplied by dH, which is nothing but the volume of this zone. This is the volume, and apparent density, if we multiply the apparent density with the volume, we will get the mass. dm is the and from there we can calculate here with this is the F is equal to mu is the frictional coefficient, apparent density of the shaft, mu is the apparent coefficient of friction, L is the peripheral length of the this chamber, peripheral length and multiplied by dh is the actual area of the contact area. This is the peripheral length multiplied by dh, it is a contact length and contact this is the contact area. So, contact area and P is the upper pressure, that downward pressure, so that is the this becomes the downward force, L dh P becomes the downward force and multiply, if we multiply the that means it will become the force, frictional resistance force. Okay. So, substituting the equation, if we go back to that 3, 4, 5, if we see now substituting 4 and 5 in equation 3, what is 4 and 5? You can see here equation 3 is the A dP equal to dm minus F, we have already derived. dm is equation number 4 is dm equal to A dH gamma and 5 is F equal to mu L dH P. So, that if you in 3, so A dP equal to dm, in place of dm we are replacing with A dH gamma. So, gamma is our target, we are trying to measure the gamma and then it becomes minus F, what is F? Mu L dH P. Okay. Now, dP it comes dP equal to, this is the relationship we are getting from that. Next step dP will be dH multiplied by A gamma minus mu LP divided by A, assuming T as the thickness of the fiber assembly, like the fiber assembly thickness is there. So, we can, the apparent density is alpha by T, that means alpha is a constant and as the fiber assembly thickness increases, that means apparent density will reduce. So, it is inversely proportional, gamma is always inversely proportional to thickness. So, here alpha is a constant. So, keeping all other parameters same. So, alpha is a constant. So, substituting equation 7 in 1, what is 1? This is equation 1 which is Van Wyck's equation, and what we are getting here, we can get pressure equal to, just we are replacing this T with this equation. So, we are replacing here with this. So, now we are getting pressure in terms of gamma, okay, that is apparent density. So, during compression the weight of the fiber assembly does not change, it does not change, hence the value of m by rho, this value is always constant, because m is the weight of the fiber, we are not changing, and rho is the fiber density. Fiber density is a constant. Okay. So, that is it is actually it's so m by rho we can consider as a constant. So, here if you see C1 is a constant from earlier we know from Van Wyck's equation, alpha is a constant, m is constant, rho is constant. So, we are getting C2, this we are all the constant we are putting one new constant C2. So, by substituting 9 in equation 8, what is equation 8? This is equation 8. So, here if we see this portion and this portion are constant C2, we are replacing C1 m by rho square by alpha square. So, all these things this portion we are taking out as C2. So, we are getting C2 E is the Young's modulus and rho square. So, that is the pressure P. Now, we are trying to differentiate, we will differentiate this in the both side, we are differentiating it. It comes out to be dP equal to 2 C2 E gamma d gamma. Okay. That is the equation 11. Now, we are substituting equation 11 in 6, equation 6. What was the equation 6? This was the equation 6, dP equal to dH A gamma minus mu L P by A. We have already derived this equation. Now, this we are trying to equate. So, this becomes d 2 C2 E gamma d gamma equal to dH A multiplied by A gamma minus mu L P divided by L. So, now we are rearranging it for dH. Okay. This is the dH, we are rearranging it for dH. So, dH becomes this. So, it is A C2 EY this divided by whole this and A will come in the numerator. So, we are just rearranging this, we are getting value of dH, H is the dH is the height. Now, substituting for P from equation 10. So, what is equation 10? Equation 10 is the P equal to C2 E gamma square C2. So, here we are substituting this P value. Now, what we get? We are getting this value here. So, this is the equation we are getting. So, what is the equation? So, dH equal to A C2 2A C2 E gamma d gamma. So, that we are getting here A gamma here getting here and mu L is there and this C2 E gamma square we are getting from this P2. We are just replacing this, substituting P. So, this is the differential equation. So, we are getting this equation as we have seen in last slide. We have just I will go back to last slide. So, this is the last slide we have got. Okay. So, here just a minute, A gamma was there. Okay. Now, here you can see here the dH. So, by dividing the numerator and denominator by of the right hand side by A. So, we are getting rearranging this with this equation. Now, here we will now integrate the both sides. We can see after integrating we are getting this value. So, this dH become H and 2 C2E, these are the constant values, okay, and d gamma integration d gamma by the denominator, this total denominator here, okay. And what we are getting? We are using this part, this as a x, this is we are using this as x. Now, differentiating both side. So, we are x is a variable or gamma is a variable. Okay. So, these two are variable. Okay. So, now, we are now trying to differentiate both sides. X we have assumed x as this is the x. So, we are now trying to differentiate both side. So, what we are getting? We are getting this dx. So, 1 is considered minus mu L C2 E by A, this is the constant, and dy d gamma equal to dx. So, this is the equation, differential equation we are getting. Now, we are now trying to rearrange this equation, and after rearranging what we are getting, the d gamma will become minus A mu L C2 by E in the all these things in the denominator and dx. So, now again we are trying to differentiate or the integrate will, because our idea is to get the gamma value, that is apparent density value. So, we are getting the apparent density, what is the now substituting 13. So, 13, this is the d gamma, we are now trying to substitute this here. So, what we are getting here? So, you can see this is the equation 13. So, H equal to, in place of d gamma we are using this. So, d gamma was A by mu L C2 E dx. So, this is being replaced here, and this was x, this was assumed to be x. So, this is the relationship by, and we are now trying to simplify. So, these are all constants, this will go outside. So, dx by x. So, you can see dx by x. So, after cancelling out, the E will get cancelled out, okay. C2 will get cancelled out, everything will, most of the things will get cancelled out here. Now, it will remain minus 2a by mu L, 2a by mu L dx by x. So, this is the h, okay. Now, here you can see h equal to log x, natural log x plus constant. This is ultimately we are getting this equation 14. Now, substituting x for 14, x we have assumed somewhere. So, this is the 14 relationship 14, and we have assumed x in terms of gamma earlier. So, now we are trying to substitute x in the 14. So, this relationship we can now see h equal to minus 2 a mu L. So, 2a mu L is there, then natural log x, x we are substituting here plus k. So, that is becoming h. Now, when h is 0, so h is 0 means infinitely small, h is height is 0, the gamma will be 0, because gamma there is no fiber and this apparent opening will be 0, but that no fiber is when it is a very compact. So, if you have a very compact, so so in that case, so h be 0 means here this is the fiber. So, if we are h is 0, there is no fiber. So, density will be 0, and if you see the density is 0 and mu is h is 0 and mu is 0, mu is 0, gamma is 0, that means this part will be 0. So, k will automatically be 0. So, for very small or tends to 0, h tends to 0, mu will be, so gamma will be 0. So, k is 0. So, k will be assuming as 0 here. So, the equation becomes natural log 1 minus this part, it is a negative part. So, this will become, this will be equal to minus this, because this will come to the other side h. So, it will come to the other side. So, that this is the relationship. So, natural log multiplied by 1 minus mu L C2 E and gamma divided by L equal to minus mu L H divided by 2a. So, this is the relationship, and from there we get this. So, natural log, if it is a log E base, so it will become, it will come out of the log, and this total portion will go to the power of E. So, that is the next step, and from there we get, you can see that you just, if we rearrange, if we actually rearrange this, so it will become, next stage is that you take this portion in the right hand side and this portion in the left hand side and rearrange, we will get this equation. Okay. That means, mu L C2 E and gamma by L equal to 1 minus E to the power minus mu L H by 2a. This is the relationship, and finally, the apparent density. Now, we can get the apparent density of the fiber assemblies will be from there. This is the apparent density, which is our target. Okay. Apparent density is our target. So, from this equation we can calculate the apparent density by this equation. This is the apparent density, where we have got everything. We know the these values, mu is known, L is known, C2 E can be calculated, E is calculated, A area of the cross section is actually known here, and 1 minus of everything is known. So, from there we can calculate the apparent density of the fiber assemblies. Okay. Now, thank you. So, we will start the new topic in the next session. Till then, goodbye.